morning and welcome to our today's lesson. We are trying to wind up on waves, and we went as far as the production of stationary waves, and we compared them to progressive waves. Probably just as a recap, a stationary wave is a wave that is actually produced when two waves of the same quality or two equal waves in terms of the characteristics that we were able to identify, that is the frequency, the speed, the wavelength, and so on, when they superimpose on each other, especially when they happen to be traveling in different directions, that is when we claim to have produced a stationary wave. Now, on the other hand, a progressive wave is one that moves continuously from the source. A progressive wave is one which moves continuously from the source. It actually moves continuously from the source. Now, we agreed that a wave is actually transfer of energy in form of a disturbance, that you disturb a medium, and once you disturb a medium, you expect that that effect is going to be transferred continuously in case of a transverse wave, or it could also be transferred in form of compressions and rarefunctions in case of a longitudinal wave. Now, those are the two types of waves that we actually measured in. Now, we agreed that a stationary wave is actually characterized by nodes and antinodes. We agreed that a stationary wave is actually characterized by a series of nodes and antinodes. So you expect that you will produce a disturbance at one end, and this one is a displacement time kind of a plot. Now, you expect that after you produce this and you fix the end, there will be a reflection of the same, so that another wave will be formed, and it superimposes. It actually superimposes itself on your original wave, resulting to a stationary wave. So, in other words, a stationary wave actually does not move, but in the real sense, you find that it's going to be characterized by a series of nodes in areas, that is, nodes in areas of zero displacement. This is also another node, and another one. Then there will be areas where we shall have maximum displacement, and those are the areas we call the antinodes. Those are the areas that we actually called the antinodes. And for that reason, the difference in the path difference between successive notes, which is also equal to successive antinodes, is actually half a wavelength. Now, this is a concept that we have really made use of when we talk about musical instruments. And musical instruments that we are talking about here are like the guitar and the piano. The guitar and the piano, they make use of vibrations of strings, and especially the guitar. Now, what happens is that we set stationary waves on the string and we play about with it to produce different sounds, as we are going to see in a bit. Now, it is going to be worth noting that for us to be able to produce a stationary wave on a string, we will have to fix both ends so that the incident wave is going to be reflected after it hits the next end. So we expect that between the fixed ends, we are going to place a string, and on it, we are going to set up a wave which we expect to reflect once it hits the second end, and that way we produce a stationary wave. So for any kind of vibration on a string, for any kind of vibration on a string, to produce a stationary wave, the ends must be fixed. The ends must be fixed. The ends of the string must be fixed. Now, once you introduce your disturbance on the point A, you expect the kind of energy that you introduce onto your string is going to be carried through the string to the other end, and then it is reflected so that it superimposes itself on the initial or the incident wave, and that one produces a stationary wave. Now, depending on the interaction that your wave is going to have, now we are talking about the stationary wave. This is the stationary wave. This is the reflected. Then we have the incident. All these are waves. Now, depending on the interaction that your wave, the final, which is now the stationary wave, is going to have with air, depending on the interaction that your stationary wave is going to have with air, a longitudinal wave. A longitudinal wave results from this So this one is going to interact with air and produces a longitudinal wave which comes in form of series of compressions and rare functions, and this one is actually manifested in form of different notes on your musical instrument, different notes on your musical instrument. Now, you have to pluck your string at some point, introduce some disturbance, let it be carried through the string to another end, upon which it will be reflected, then interact it with air so that you can have different notes. Now, before we go to how we can be able to produce the different notes, we have some terms that we are going to use in the course of our discussion, and we think we should actually understand them. Number one is the fundamental frequency. In the course of our discussion about vibrations on a string, we are going to come across this term, and this one means the lowest frequency. The lowest frequency that can be produced. By a musical instrument. Now, we have been able to discuss, and we have seen that depending on the frequency and other factors, we are going to produce different notes or different sounds, if you may. Now, the lowest frequency that we can achieve is what we call the fundamental frequency. However, it is good to note that different instruments have different fundamental frequencies. They have different fundamental frequencies. You do not expect a guitar that is designed to produce one note to have the same frequency as the other one, which produces a different note. Now, this fundamental frequency, we write it as F naught, F subscript O, meaning F naught, or our simplest or lowest frequency possible. Now we will also look at another term which we are going to call an overtone. An overtone. And an overtone, this one is another, or let us use a pronoun. Overtones, these are other sounds of higher frequency than the fundamental frequency that accompany, they actually accompany the fundamental frequency. That when you are playing your musical instrument, you will produce your simplest frequency, which we are calling a fundamental frequency, which will come in form of a note. However, you do not expect that the fundamental frequency will be the only note that will play in your musical instrument. Rather, you will have some other sounds, background sounds of different frequencies, and these ones are usually higher than that of the fundamental frequency. They will accompany your simplest note, which we call the fundamental frequency. And why do we bother to include the overtones? The overtones actually, they determine the quality. They determine the quality of sound. They determine the quality of sound produced by a musical instrument. They determine the quality of sound produced by a musical instrument, and for that reason they are of utmost importance. We will also look at another one, which we call a harmonic. When we are discussing a musical instrument, a harmonic refers to other notes whose frequency is a whole number multiple of fundamental frequency. They are actually notes whose frequency is a whole number multiple of fundamental frequency. By whole number we mean that frequency F1 of the first note will be, say, X F naught. The second one will be 2X F naught, and you can continue to infinity depending on the number of notes you have for your instrument. Now we move a notch higher and look at how we can produce, fundamental frequency on a vibrating string. We look at how we can produce fundamental frequency on a vibrating string, and here we fix both ends, and then this one is a fixed end we are going to call A. Then we have another fixed end, we call it B. Then we can have our string and we can pluck it at the middle to produce only one loop, and we expect our loop to be reflected on the other end, so that now we can produce a stationary a stationary wave. This one is the incident. This is the incident wave. This one is the reflected. Is the reflected wave. Then we can call this one the stationary wave. Now, one thing we have to note is that we have to fix both ends so that we can have a reflection once we come to the other end. And then we hold our string at the center and pluck it from the center, have a loop produced which is half a wavelength. Then when it comes to the fixed end that we have marked B, we are going to have a reflection of the same which superimposes itself on the first loop to form a stationary wave. Now, let us assume that this length is L. This length is L, and we have fixed the ends. We have fixed the ends of the string. That means that here we have zero displacement. Zero displacement. Zero displacement is what we call a node, and so will the other end be. Now, clearly, this loop is half a wavelength. This loop is half a wavelength, so we can assume that our length L is half the fundamental wavelength. L is half the fundamental wavelength, where the fundamental wavelength is actually the simplest wavelength that you can produce and which accompanies the fundamental frequency. Now, but we know that speed of a wave is a product of its wavelength and its frequency. Speed is actually a product of the two. Therefore, we can substitute for our wavelength. In this case, if L is half the wavelength, then it means that our wavelength is actually equal to 2L. Therefore, if we substitute this in our equation, it becomes V equal to 2L F naught. But we are interested this one is L. We have our stationary wave there. Then we have the nodes, areas of minimum displacement. We have the antinode at the center. Again, we have a node at the end. This length, we call it L. And then we note that L is actually half a wavelength, half of fundamental wavelength. Therefore, this one implies that if L is equal to half the wavelength, then it means that the wavelength is equal to 2L. Now, but we know that speed is equal to the frequency multiplied by the wavelength. And in this case, we have fundamentals. We have the simplest frequency, the simplest wavelength that we can afford. And therefore, we want to substitute. We want to substitute for wavelength in our equation 1, and we will achieve something like this. V will become F naught 2L, and then we are interested in getting an expression for our fundamental frequency, so we make it the subject of the formula, so that now it becomes V over 2L. It becomes V over 2L. Now clearly this one is an expression of fundamental frequency in terms of the fundamental wavelength and the speed of our wave that we have produced. I will go through that again. That we had a string whose ends were fixed. Then we pluck it at the center. Please note that the point where you are plucking your string is going to be very important, because it informs the kind of frequency that you want to come up with. And in this case, we want the simplest possible frequency that we can afford, and which we have called the fundamental. So we do it at the center and make sure that our ends are fixed. Therefore, we produce only one loop, which is actually a crest. And when it comes to the second fixed end, it is actually reflected, and it superimposes itself in form of a trough. Now, clearly, the amplitude of the crest is equal to that of the trough, only that now the two are moving in different directions, or we can say they are out of phase. They are actually at different levels of displacement. Therefore, when they superimpose, now they form a stationary wave, which we have represented using the dotted line. And if the length between the two, the distance between the two fixed points, we called it L, and we have produced only one loop. Remember, for a wavelength to be complete, we have to have a crest and a trough. This time we have only a crest, which translates to have a wavelength. And we have used that to come up with an expression for our fundamental wavelength. And we considered the relationship that we already looked at earlier on, where we actually discovered that speed of a wave is a function of both frequency and wavelength. This time, remember, we are working with our fundamentals. Therefore, we can substitute for the wavelength. The expression for the wavelength, where we got it as star, then we can feed it into the relationship that we have, and that way we come up with an expression of our frequency, which is actually fundamental, in terms of the wavelength as well as the speed of the wave. However, we have been able to see that if we played the fundamental frequency alone, then the quality of the sound produced by our musical instrument is actually going to be compromised. Therefore, we always consider some overtones and some harmonics, where we have seen that a harmonic is actually a note whose frequency is a whole number, a multiple of the fundamental frequency, and an overtone is actually that sound that will accompany the fundamental frequency and which will have an effect of informing the quality of sound that we desire. Therefore, let us try and discuss how we can produce first overnote, which we will call the second harmonic. This one is actually the second harmonic. Why the second? Because we said that a harmonic is actually a note whose frequency is whole number multiple of a fundamental frequency. Therefore, the first whole number on our number line is 1. If you multiply that by the fundamental frequency, gives you the fundamental frequency. Then you can go to 2F0, which now becomes our first overnote, because it is the first note with a frequency higher than the fundamental, but the second harmonic, because we have multiplied it by the second whole number on our number line. We could also consider the third, the fourth, and so on and so forth. Therefore, the fundamental frequency is actually the first harmonic of a musical instrument. Now, the first overnote, the first note with a frequency higher than the fundamental, now becomes the second harmonic. Now, how do we produce this? Again, we fix some ends. Fix some ends have our string between end A and B. We have a distance L. Then we hold our string, hold the string at the center, hold the string at the center and plug it at a distance quarter-way from one end, quarter-way from one end. Now what you produce will be something like this. That you've held your string at the center, then you want to plug it at a distance which is quarter-way from one fixed end, so that now you produce an incident wave which comprises of a crest and a trough. Hold it at the center, pluck it at some point quarter away from one end, that is a quarter of L, and what you produce will be a wave which comprises of a crest and a trough. Now, once this wave comes to the other side, you expect that it's going to be sent back and superimposes itself on the first one, so that now the result becomes a stationary wave. Again, we have a stationary wave. This time we have 3 nodes, areas of 0 displacement. Then we have 2 antinodes, which are areas of maximum displacement. Now, here at the ends, air is not moving, the string is also not moving. That is why we say that at the fixed ends, we will always have a node, because neither the air nor the string at that particular point is vibrating. Now, when we produce the stationary wave, clearly we can observe that now we have a complete wavelength. We said that for a wavelength to be complete, it has to have a crest and a trough. In case of a transverse wave, then we should have an area of compression as well as that of rarefaction in case of a longitudinal wave. But again, we said that once we produce the stationary wave, which is in form of a transverse wave, we do not expect that this particular instrument is being played in a vacuum. Rather, we are playing it in a place where we have air. So we expect that our string is going to interact with air, and for that reason, our stationary wave is now converted from transverse to longitudinal. And now, depending on its characteristics, we are going now to have different notes or different qualities of sound. Now, here, we note that the wavelength now, which we are going to call a wavelength 1, that is the first overtone, is actually equal to L. Is actually equal to L, because the length between the fixed ends is actually accommodating a full wavelength. Now, we can go ahead and get an expression for the frequency of the first overtone. The first overtone for the first overtone, and we say but speed of this wave now will be a function of the first wavelength and the first frequency. It will actually be a product of the two. Now, if this be the case, we can substitute for wavelength, so that now so that now speed becomes L F1, and therefore the frequency of the first overtone becomes V over L. This one is the frequency of the first overtone, or what we call the second harmonic. Now, but we want to compare it with the first frequency, the fundamental frequency, find whether there is a relationship between the two. But before we do that, let me quickly go through the steps we have taken to get here. That we have used a string, we hold the center, and we pluck it at a point which is quarter way from one end. We produce a wave which is actually comprised of a crest and a trough. When it hits the other fixed end, it is reflected so that it superimposes itself on the first one. The result of that is a stationary wave, which we expect to interact with air to produce different qualities of sound. Now, clearly, between the two fixed points, we have a distance L, and therefore, we have equated our wavelength to L, now that we have a complete crest and a trough, which represents a full wavelength. Therefore, that becomes our first expression of the first wavelength, which now we incorporate in the relationship that we already know, substituting for the same so that we have an expression like this. But now we are interested in expressing our frequency as a function of wavelength and speed. That is why now we made F the subject of the formula. Now, but from the expression of the fundamental frequency, F naught we said is actually equal to V over 2L. We can call that one equation 1. We can call this other one equation 2. And we want to compare. So write comparing 1 and 2. 1 and 2. We find out that we can compare by taking F1 over F naught will actually be equal to V over L multiplied by 2L over V. We can cancel where possible, so that now we see that F1 over F naught will become 2, implying that actually F1 is equal to twice F naught. F1 is actually twice F naught. F1 is twice F naught. Therefore, if you had an expression of the fundamental frequency, you need not derive that of the first overtone. Rather, you can just substitute and multiply your results by 2, and there you will have landed onto the frequency of the first overtone, which we must appreciate is our second harmonic. Our second harmonic. Now, we look at the second overtone. Let us try and get an expression of frequency of the second overtone. Let us try and get the expression of the second overtone, which in this case will be our third harmonic. Now, the difference between the waves that we are generating here is actually the point at which you pluck your string. Like now, I will fix the two ends again. Fix the two ends. Have a distance which we are calling L between the fixed ends. I hold my string, hold the string at the center. Hold the string at the center and pluck it at a point that way from one end. You again hold it at the center, pluck it at a point a that way from one end. Now what happens, you will have now a crest, a trough, and another crest. You will have 3 loops, 2 of which will be crests and 1 will be a trough. Again, take it to the other end. You expect that we are going to have a reflection of the same, so that now we form a stationary wave. We have a reflection. You will have a reflection of the same, so that now you have, again, you generate a stationary wave of that nature. Now, always at the ends, we have the nodes. Nodes, if you wish, are areas of zero displacement of particles of air, as well as those of the string. You will have another one, and another one. Now, we said that we will always also have the antinodes. We will have them like that. Now, clearly, you have a full wavelength and a half. A full wavelength for a transverse wave comprises of a crest and a trough, and we have 2 crests and 1 trough. Therefore, we only have 1.5 wavelengths. Therefore, L in this case will be equal to 1.5. This time we call it wavelength 2, is that of the second overtone. That is why we call it 2. And therefore, L is equal to 3 over 2 of the wavelength, implying that wavelength is equal to 2/3 of L. 2/3 of L. Now, but we know that V is equal to the wavelength multiplied by frequency. Therefore, we can start by substituting for this so that V becomes 2/3 L multiplied by the second frequency, or the frequency of the second overtone. And therefore, the second frequency will actually be 3/2 L 3/2 L V. 3/2 L V. That is the expression of the second frequency. Second frequency, or the frequency of the second overtone. We go through it again, that we hold the center of the string, pluck it at a point which is a third way from one end, and then we produce a wave which comprises of 2 crests and a trough. Take it to the other end, have it reflected, superimposing itself on the first one, so that now we can have a stationary wave which is formed after the interference of the two. And the distance between the two ends again is L, which implies that L will be the size of 1.5 of the second wavelength. Then we can, from there, we can make the second wavelength the subject, so that we come up with an expression of this nature. Now, from the relationship that we discussed, we can feed in the value of our wavelength 2 and substitute it into our relationship, so that now we can have something like this. Make F2 the subject of the formula, and therefore we can come up with something of this nature. Call it equation 3. Expression of the third frequency, which is the frequency of the second overtone, or the third harmonic. But we want to compare it. Compare equation 3 to 1. Compare equation 3 to 1. Remember, the equation we are calling equation 1 is that of fundamental frequency. I will remind you that fundamental frequency is actually given by V over 2L. And now we are comparing the two by way of division, where we will have F2 over F0 will be equal to 3/2 LV multiplied by this time the reciprocal, so that now we have multiplied by 2L over V. We cancel where possible, so that F2 becomes 3 times F0. F2 becomes 3 times F0. Now, there is something we are going to discover. There is something we are going to discover. Our first equation, which was an expression of V naught, was actually, that is F naught, sorry, was V over 2L. We call that one equation 1. Then we came to the second equation, which was an expression of F1. We say that F1 is actually V over L, and this one we said is twice F naught. After comparison, we found out that F1 is twice F naught. Now 3, the one that we have just derived, we have found out that F2 is actually 3 over 2L V. 3 over 2L V. And this one, we've said again, is 3 times F naught. We have said it's 3 times F naught. So what are we trying to say? If you look at these relationships, this one, let us call it 1 F naught. It is actually giving us some trend. This relationship is actually giving us some trend. Suppose we go on so that now we can have Fn. I want to be sure that it is going to be N over NL, that is N plus 1 over NL. See, this is F2. We are taking the 2 to be our N. In this case, it becomes 3. So 2 becomes 3. Therefore, N plus 1 over the 2, which is our N, 2L, then V. So that will be the expression N plus 1 over NL, then V. And it will be N F naught. N F naught. Therefore, what we are learning is that for the nth overtone, sorry, for the nth overtone, Fn will be equal to N plus 1 F naught. N will be equal to N plus 1 F naught. So, back to our definitions. We looked at the fundamental frequency and we said it's the one we are abbreviating as F subscript 0. F subscript 0. And we said that is the simplest possible frequency that you can come up with in a musical instrument. We found its expression. Always recall always recall V is equal to F. Always recall that relationship. It is of utmost importance when it comes to getting the expressions of these frequencies like we have just seen. We always apply it. Then you compare them by way of division. Now, clearly, the first fundamental frequency is the simplest. Even from the expressions, you can be able to find out that it's actually the lowest frequency. However, other frequencies can also be expressed as functions of fundamental frequency, and that is where now we came up with the word harmonic. Harmonic. That a harmonic is that note which has a frequency which is a whole number multiple of the fundamental frequency. And whole number multiples, on the number line we have 1, 2, 3, 4, 5, and so on up to infinity. Now, the first frequency, which we call the simplest or the fundamental frequency, has a multiple 1. Whole number multiple of fundamental frequency. That is why it qualifies to be the first harmonic. It follows then that the second frequency is a 2. Is a 2 times multiple of fundamental frequency. The third will be 3 times the fundamental, and so on and so forth. So you can label them as harmonics as you progress. However, it should be noted that an overnote must have a frequency greater than the fundamental, and that is why an overnote is the second harmonic and up to infinity. Now, that's about all to do with vibrations of a string. When we meet next, we shall find out, does air column vibrate in a pipe? And if it does, how different is it from the vibrations of a string, and how can we apply it in form of a wave? Thank you.